We move on to question 19. A long straight wire carries current I. Do you have an expression for the magnetic field at the point of distance r from the wire? So this is what we have discussed in the syllabus, and it is about the Ampere's law, where we state that the sum of the length element multiply the magnetic field perpendicular to the length element is equal to the permeability multiply the total current enclosed. So just substitute the total length element is 2 pi r, the circumference of a circle. In the end, we have the magnetic field is equal to mu naught I over 2 pi r. We move on to question B. A long wire which carries current of 2 ampere is looped in the form of circular coil of radius 5 cm with 100 turns in the vertical plane as shown in the diagram below. So determine the magnitude of the magnetic flux density at midpoint X between the wires and the center Y of the coil. So the first one is pretty simple because we have just derived the formula, which is the mu naught I over 2 pi r. So from here, using the right-hand grid rule, first we can obtain the magnetic field due to the wire on the left, which should be in this direction. And also for the right side, okay, it's also provided in this direction. Okay, just use your right hand and you can obtain the direction easily. So from here, we can see that both the magnetic field will be stacked. So since they have the same current, so what we have just apply the formula mu naught I 2 ampere over 2 pi r. So the r is the distance from the point X to the wire. So we know that the circular coil have a radius of 5 centimeter. The distance is also 5 centimeter. And then we times 2 because they are stacked together, okay, because they are in the same direction. So it will be plus. Okay, so then in the end, we can have the magnitude at midpoint X is 1.6 times 10 to the power of negative 5 Tesla. And as for the second question, we have the center of the coil, which is the circular coil. So you need to memorize the formula, which is given as mu naught Ni over 2R, where N is the number of turns. So what we have is we have the mu naught for 4 pi times 10 to the negative 7 multiplied the number of turns, 100 turns. And then we have the current 2 ampere over 2R. So in the end, we shall get the answer of 2.51 times 10 to the power of negative 3 Tesla. We move on to question C. Uniform magnetic field acts on the straight wire that carries a constant current I and an angle as shown in the diagram below. So sketch a graph of the magnetic force against the angle from 0 to 180 degrees. So I think this should be something not too difficult. So we have the formula of the magnetic force is ILB sine theta, okay, where the theta is the angle between the magnetic field and the current. So we know that when the magnetic field and the current, when they are in parallel, so there should be no magnetic force, and it is maximum at an angle of 90 degrees. So this should be a sample answer for your own reference. And I think we can move on to question D. Horizontal copper wire of length 2 cm, diameter 1 mm, carries a current of 2.5 ampere, is placed in the middle of a long solenoid perpendicular to its axis. So this is something that you need to take note, perpendicular. The solenoid has 4,000 turns per meter, so this should be the number of turns per length. Okay, carries a steady current I. Calculate the current in the solenoid if the magnetic force on the copper wire is equal to its weight. So you're given with the density of the copper. So from overall, you need to think of how is this, what is the current situation in this question. So I will try to draw. So this should be a rough illustration, not so accurate, but this should be enough for the analysis of the question. So first of all is that we know that the magnetic force is equal to its weight. So the weight is always in the downward direction. So we could expect that the magnetic force produced should be in upward direction, okay, as we have learned about the Fleming left-hand rule. So overall, what we can see is that the current and the axis of the solenoid, okay, is in the perpendicular. So you learn about how the magnetic field is produced in a solenoid. So this should be a rough diagram for your own imagination. So roughly go through, we have the weight in a downward direction, which is equal to mg. So we are given with the density, and if you look carefully on the first statement, we have the length of 2 centimeter with a diameter of 1 millimeter. So this should be enough information for you to get the volume, which you can multiply the density to obtain the mass of the copper. And then the next thing is that we need to find out the magnetic field inside the solenoid, which is also one of the formula that you need to memorize, which is given as mu naught Ni, where the N is the number of turns per length. So we just put in all the values here, and we can obtain the magnetic field is about 1.26 times 10 to the power negative 2 Tesla. And as for the way as what I have explained just now. So put in a raw Vg, we have the density multiply the volume, which is given as the length of the wire, multiply the area, which is pi r squared, and then multiply the 9.81, and we can obtain the weight of the copper wire is about 1.39 times 10 to the power negative 3 Newton. So to conclude this question, that we have the magnetic force is equal to the weight of the copper wire. So the magnetic force is equal to ILB, where you should not be confused with these two current. First current, IW, is the current inside the wire, which is 2.5 ampere, and the current in the solenoid is what we need to find in this question. So it is in the formula of FB, ILB. So I is referred as the current inside the solenoid, multiply the length of the copper wire and the magnetic field, and we can obtain that the current in the solenoid should be equal to 5.52 ampere.